Good evening, sir.
Good evening. Hello, am I audible?
Yes,
Yes.
sir.
Okay. So I think we wait for a few minutes and think nobody's joining. So we'll start now. Okay, so let's begin. And so before starting, do you guys have any doubt from the previous classes or any questions that you had from the last classes or any doubt you can ask? No doubt? No doubt. So, did you try solving your all questions? Okay, if no, then we'll go ahead. So let's start with our this session. So I hope I'm audible to you guys, and if not, then please let me know. So yeah, good evening, everyone. So welcome to the week 3 of our doubt and problem solving sessions in the NPTEL course of Carbon Materials and Manufacturing. So I'm Saurabh Soni, and today we'll be solve some questions and try to clear some concepts related to the whatever covered in our week 3 lectures. So I will be giving or I will be throwing some questions and we'll discuss, and if you guys have some doubt then you can ask there, or later on also you can ask. So yeah, so this week mostly what I observed in this week 3, we basically learned about the crystal structure and some Miller indices, and how they are arranged in what form, and there are then something related to the heat treatment and your some needle coke and all. There are, I mean, many concepts that are very interesting in this we found in this week, and it will be helpful for you if you know this basic knowledge. Then it would be very helpful for you to have a better understanding about the graphite. So starting from this carbon materials, if you observe that we are gradually moving towards the graphite, so basically we were covering all the crystal structures and manufacturing and all of this material which is called graphite. Okay, so now I'll begin with the questions directly, and in the questions I will be discussing about that. Okay, so the first question is two main parameters that determine the quality of graphite. Okay, so basically whatever, suppose as a material scientist, whatever material we have, so ore is what, from where we are getting our materials, if you know, I mean, in a very general or broad term. Okay, so like metal. So even if you know the ore means basically what, suppose you have a copper is a metal, but in a earth crust or from where you are getting copper, so it will not be in a pure copper form, okay, it will be in a ore form. So you have to do a lot of processings, and many steps are there which is involved to get the copper. Okay, there are tin. So as a metallurgical engineering and material scientist, you have to know that what is the ore of which material. Okay, so here the main question is the two main parameters. There are a lot of parameters which will determine the quality, right? So I mean parameters if you will say, but here it is asking in the perspective of a material scientist. So if you want a good quality, then what should be the two parameters of the graphite ore? So first one is crystal size and purity, LA and LC. If you have been through the lectures, then you would probably know that what is LA and LC. Crystal size and manufacturability, compatibility with froth flotation. So if you have heard about the flotation technique, so which is basically if you have learned any subjects which is related to minerals and ore beneficiation, okay, where you will get to know that how this material can be I mean extract from their ore. So there are many steps are involved. So in that steps, froth flotations are also one of that technique. Okay, so
Yes.
compatibility with the froth flotation. So can you guys give if you have been through the lecture?
Crystal size, purity, and La by LC value.
Okay,
Second option is La and LC. That is
okay,
crystallite diameter, stack thickness.
okay. So why can you give me the answer of your any reasoning that why you are choosing this answer?
Sir, La and LC will define the crystal size only eventually, and that will tell us like the layer spacing, how much graphite has, if it
Okay,
is set.
okay,
The
okay,
length values along A axis, and that is basal plane, and C axis of a crystal LC.
okay. So one is saying I think crystal size and purity also and LALNC, right?
Yes.
Yes, sir.
So yeah, let's see in the lectures that what was there, that what we learned in that and some corresponding slides. So basically, in this slide you will see engineering carbon. Okay, so engineering, there is a term in carbon, there is term called engineering carbon. So where the term engineering attached with anything, so you have to know that something is happening or something is cooking. Okay, from there only the engineering terms will come. Okay, we are extracting, but here that is first one is natural graphite. Okay, so we have to know that what are the properties, and through that specific property why we are using so much this. So engineering carbon is basically the carbon material used in large scale manufacturing. This excludes micro nano carbon structures materials. So carbon manufacturing is basically has two aspects. Okay. So first in is processing or making the material itself. Right. So how we have to any material before getting it in the end product, we have to process that material. And second is making structural components. Okay. So first thing we deal with the material. So we have to sorry. So firstly we deal with the material. So to make the material, we require some process. After getting the material, what we have to do, we have to, so suppose if you got the material, then what you have to do? You have to design some device or whatever you want now towards your end product. Okay. So suppose you have a graphite or graphite or graphene, but only material is not sufficient. You have to utilize that material to make your design of your device. So making structural components or device using the carbon material. So that is your end goal. Now there are certain example of the engineering carbons. So like graphite. So graphite is basically natural and synthetic. Granular porous carbon, activated carbon, carbon black, glass like, or the glassy carbon. Often we heard this name. Even I also do not know that how it looks, that glassy carbon. But many this I have seen some people are using this for this energy storage and to reduce chemically something or some as a catalyst or like that people are using. And carbon fibers, carbon resin components, carbon resin composites, carbon composites, etc. Okay, so uh, just wait for a second. I'm just trying to get the marker, but I do not know how to it is coming, but in a presentation mode. Mm, okay, let's have fine. Hello, am I audible?
Yes, sir.
Yes, sir.
Okay. Sorry for this glitch. Actually, I want this marker. I have downloaded, but I'm not getting it now. How to do the slides? So, okay, fine. If it is also not coming, then not a big deal. You can do it. Just wait for a 1 minute.
Sure, sir. Sure.
So, yeah, I hope now I will be able to draw something. So, voice is coming, right?
Yes, sir.
Okay, okay.
Yes, sir.
So, actually, I was getting this my uh, digital pen to if I want something to write. Okay, yeah. So yeah, where we were. So okay, so these all are the materials which are available. Carbon example of the engineering carbons. Okay, so right now the okay, so the next thing is your natural graphite mineral. So mineral, if you have been through your basic material science or the metallurgy, you will know, you have to know. So if anybody know that what is the difference between ore and mineral?
Sir, ore contains lot of impurities. Mineral is what is obtained by refining the ore.
Okay, okay. Anybody else? So yeah, that is also right, but you can also define in many perspective. So if I will give you one statement, so can you say, like a vice versa? Can all mineral can be ore, or all ore can be a mineral? Which one is true? Okay, fine. Mineral is
All
something that,
minerals are derived from ore.
okay, okay. So yeah, so there are many new terms which are coming. So natural graphite mineral ore. So here you can see the metamorphic sedimentary rocks. Again, the new word came, right? So if you will know that, if you will there is one book, I forgot the author, that minerals and ore beneficiation. If anybody are from the metallurgical department, then you will probably know that there are several types of rocks, metamorphic, sedimentary, and all. Even I also do not remember all those examples. So example embedded in mica. So mica is also a one kind of a, if you know, what to say, ore kind of material. So there you will get extract something, and there is a marble and quartzite, and in elemental form with impurities. Okay, so there are still some impurities, it's not something that is very pure. So metamorphic sedimentary rocks, then what is metamorphic rock? A rock that has transformed into another form due to high pressure. Okay, so in the earth crust where the pressure is very high, or the temperature inside the earth crust is also very high. Okay, so there only your metamorphic rock will form. It is also formed by thermal metamorphism in coal seams, a small crystal. Okay, so I think you have to see, because this is a very new term for me also, coal seams. So there is some term called thermal metamorphism. So thermal is, it is somewhere related to the temperature, where I think some high temperature will be given, and then your something coal seams called thing will form, and that will have a small crystals. So it is formed by the removal of non-carbon atoms from organic material under extreme conditions. Okay, so graphite ores are classified based on impurities and crystal size. Okay, so this is the thing which we were looking for in the question. So if you have a graphite ores and they are classified on based on what? Impurities. So any ore, so if it will have a high amount of impurity, let's say a very high, then you have to do a lot of process. Okay, and crystal size will also matters, because for the end product, what will be your crystal size, whether it should be a big or it should be a, I mean, small, whatever the crystal size you want, that will also matter, because that will only define your property. So here it is giving some um, India produces some factuals. So here it is saying that India produces of 50 to 20% of percentage of your world's graphite. Himalayan graphite is known for its large scale. This is of high interest to geologists. So this is something that is not much of our use. So yeah, Himalayan graphite. I also got to know that in Himalaya, graphite is also, you know, found there. So this is the one thing. So yeah, so graphite ores, impurities and crystal size. So what was there in our, oh sorry, what is happening? Uh, so crystal size, purity, that will matter, and La and Lc that you guys said, but we have to see, because as per this slides, firstly the crystal size and impurity. So you can also say the impurity will also matter. So, but let's see La and LC, if some in some slide it will come, then we have to see. But yeah, crystal size and purity is for sure. Okay, so I will also see about the La and LC, which I will discuss in the further slides. So the next question is your about your a Berger vector indicates. Okay, so Berger vector indicates what? The location of stacking fault. So first of all, what is Berger vector? I mean, that is the question. So what it will indicate? Do you know what is Berger vector?
Yes, sir. Burgess vector is that vector which
Hmm.
is used to describe different dislocations or you said defects of in a crystal structure,
Hmm.
and this vector is like it is added like throughout the crystal, like the total Burgess vector is taken.
Okay. My diagram is not very good, but do you guys remember something from this diagram? What kind of a dislocation it is? Anybody?
Screw
Hmm?
dislocation.
Huh?
Screw dislocation. Screw dislocation.
Are you sure?
I think so.
How many dislocations names do you know?
Line dislocation, plane, twisted planes.
Have you know this word?
Yes, sir.
So now what is this dislocation?
Edge dislocation.
Yes. So now I will give you one task, guys, so that you can brush up your basics. Okay. So in the next class, I will ask you about any one of you that learn about this dislocation, about screw dislocations. I know maybe it is not of your use, but still you have to learn this because it will come. Because if you want to know the basic material property wherever you are something related to, I mean, defects or something will come, then you have to know that what is the edge dislocation, what is the screw dislocations, how many types of screw dislocations, how this edge dislocations is forming, and how this screw dislocations is forming, and I mean, all the things related to that. That's it. Okay. So basically, so here it is saying that so the location of stacking faults, magnitude and the angle of the dislocations. So yeah, again the term called dislocation. So you have to know the dislocations. So if anybody wanted to know that what book they want to prefer, or everybody knows that the book they want, do you guys know from where you can read this all?
Solid state physics. Pillai.
What?
Solid state physics.
No, no, no. What is the name of this author? Anybody knows?
Callister.
Yes. So if anybody is not from the materials or metallurgy background, just to have a basic introduction, there you can find. Okay, so this is one book. There you will find in a very basic term. If you want to go in a very deep, then do you guys remember this book or not? No?
No, sir, I'm not from metallurgy background.
Okay. Okay.
No, sir.
No, you don't know this mechanical metallurgy? Okay, sorry. So I was expecting much and I was asking that what is this dislocation? Okay, I'm sorry guys for that. So it's not that. So yeah. So please, you can find this in online. So you can just write this book, or if you have some library access, just go there and you can find some hard book also. So first thing is Introduction to Material Science by William D. Callister, and Mechanical Metallurgy by George E. Dieter. Okay. I had sometimes earlier the hard copy, but I do not remember now. Okay, yeah, fine. So there in this you will find all your concepts related to the defects and edge dislocation, screw dislocation. It is very highly recommended book. Okay, so there you can find. So yeah, so I will ask in the next class that about this dislocations and the Berger vectors. So yeah, so here I will take a very basics, the magnitude and the angle of a dislocations. Okay. So if any material, okay, so let's say in the terms of this rhombohedral graphite, I mean, I will also in the upcoming questions I will discuss about this how many types of crystalline structure of the graphites are present. As you can see, the hexagonal and rhombohedral. So rhombohedral graphite is a metastable state, and hexagonal is the thermodynamically stable. So Rg is always found along with Hg in nature. In Hg, it means hexagonal graphite, the corner atom of layer B. So you can see here A, B kind of layer will be there. B layer is attached at the center of A. Okay. So here as you can see what it is, what this want to say is that uh, okay. So sorry, this is the B atom. Okay. So this is a B layer. So this is B, in B layer you can see here this is corner, I mean corner atom of layer B is at the center of A. So here you can see it is at the center. Again, it is at the corner, and at the A it is at the center. So this is the center, this is the corner. Okay, got it. So now up to 25% of graphite may have rhombohedral structure. Mostly we found it in uh, I mean this what to say, hexagonal graphite, because it is thermodynamically stable. So graphite almost never has AA structure. Okay, you won't find that the corner atoms, I mean in the graphite, the corner, this atom, so you won't find like this. Okay, so AA it means to A, and this will also not be, it will also be a same structure. Okay, like this, like this. So it will always have this center and corner kind of a structure. That why it makes a AB kind of a layer. So and due to prohibitive energy reasons, unhybridized p orbital. Rhombohedral graphite is often considered a stacking fault since it can form by glide or twinning. Again, the new term came. Graphite basal planes in the main glide plane. So I'm not. If I will explain that, may not, you may not be go and read. So that's why I want you guys, so that in the next class I will be probably taking up one of the sections on this all. I will try to take if time will permit. So again, do you guys know that what is glide and twinning?
I don't know exactly, but there are different types of boundaries, grain boundaries.
No, that is alag. You are saying about the twin boundary or like, no, it is something else. If you will, so in the same book, in the detail only, mechanical metallurgy, so you have to see what is stacking fault and what is the glide and what is twinning. Okay, so you will know there is something how there is arrangement of atoms, so how the glide and twinning will occur. Okay, so we'll discuss, don't worry, but I will give some time, so that's why I don't directly want to discuss and put all the things in your mind, because this is something, if you have some prior knowledge, then it will be a very easy to learn, right? Now, the basal dislocations. So, Berger vector parallel to the basal planes. Okay. So, basal planes are something through which the glide will take place. Okay. So, in any kind of a crystal structure, if I will give you a HCP or the hexagonal closed packs, then you should know that what is the basal plane of this. Okay. Through which the dislocation will take place. So, or more common in graphite. Now the Berger vector comes. So Berger vector, so it is a vector. So usually we define this like edge to location or screw dislocation. So edge is like this. This is positive edge dislocation. This is negative edge dislocation. So few times ago I just draw this kind of a diagram. So this is your positive edge dislocation. Why? Because it is formed like this. No. Okay. So this is positive and this is negative. So that represent the direction and magnitude of the dislocation. So here if some dislocation will, then what will be I mean direction means in which direction the dislocations are going, and the magnitude. Okay, what is the magnitude of that dislocation? Its value remain constant at all points of the dislocation. Okay, so this is something that that is very common. Now rhombohedral graphite is mainly studied for defects in graphite, but has also been proposed as a graphite with optimum angular spread for certain applications such as superconductivity. Okay, it's electrically thermally conductive and anisotropic. So this is saying about this rhombohedral, that this is a superconductive and it is also anisotropic thermally and electrically. So if you will see that what is the difference in the rhombohedral, so here you can see how the atoms are arrangements. But if it would be like a hexagonal, then it would be like this. Okay, so yeah, so now, yeah, so what was our question? uh, so our question was, a Berger vector indicates the magnitude and the angle of the dislocations. Okay, now La, now that question came, that what is La? So La of the graphite crystallite is measured in the form of what? Do you guys know this thing? Or let me download this thing. Where is the download option? Okay, fine. Do you know? Hello?
Yes, sir.
Okay,
Sir, the diameter of equivalent spheres measured.
just a second. 122. Fine. Now I think I can draw this. Okay. Yeah. Okay. Better. Yeah. बताओ. Huh. So somebody was saying something. Sorry. I could notice that. So alien graphite crystallite is measured in the form of what? Diameter of an equivalent sphere, radius of an equivalent sphere, diameter of an equivalent circle, or the radius of an equivalent circle. What?
So the diameter of an equivalent sphere
Okay.
measured, LA measured in a diameter of equivalent sphere.
Okay. Fine. So yeah. So the graphite crystals. So natural graphite crystals. So basically, it has a this two crystallographic forms, which I said in the previous slide: the hexagonal graphite and the Hg
Rhombohedral.
and rhombohedral. Okay. So hexagonal graphite crystal is what? Hexagonal, by the name itself, it is clear. Okay, hexagonal crystals, but does not feature. So it is not the hexagonal closed pack, right? There is a difference. It is not, please be, it is, but SCP is what? Hexagonal closed pack. Now again your basic skin here. So if you know that hexagonal closed pack, what is, I mean, how this looks, or what is SCP crystal structure, you know, right? You know this
Yes.
all. Somebody here who is not aware of these things? So it means that everybody knows, right? So yeah, if not, then again the go to the basic your introduction to material science. So so yeah, um, again, so in
Sir, one
SCP,
line,
what?
sir, layers are separated with an offset. Sir, what is that meaning, sir?
Where layers are separated with
Are,
an offset. So offset is what?
sir,
When,
कमी पूरी करना, I think.
no no. Offset is not here. The layers are separated, so you can see now here A layer, B layer, C layers. So in the previous slide, if you remember, so it has this thing now. Yeah. So here if you can see, this is one layer and this is another layer. So here if you will see, then it is center, so there will be some angle, right? If you will
Yes, sir.
see, then this is at some angle, so there will be some offset term will become because of this angle. So that's why it is separated at some offset. I mean, most probably this is saying in that concept, because here if you will see, here again the same thing will come here. This is a corner atom. Okay, so this will come to the center of your this atoms. So again this is a center, so this will attach to the corner atoms, right? Now, so in the SCP, your C value is 1.633 A. So A is basically this term. So A is 0.246 nanometer, and in graphite the C value is 2.723 due to unhybridized p orbital electron cloud. So if you remember, we have know that what is unhybridized p orbital in our previous lectures. We have seen electron cloud, that how the electrons are, there. So due to which the conduction will come. Now the unit cell constant A is 0.245 and nanometer, and C value is also given. So separation between layer AB. So if you will do the separation, so here the separation will come to,
Half of the C value.
yeah, half of the C value. So here it is one layer and here it is two layer. So if you will do from here to here, so it will be your 0.670
335.
by 2. Okay. So,
Yes, sir. 0.335.
okay. So now the bond length between the adjacent carbon atoms, um, bond length is given 0.142 nanometer, space group is given, and stable up to something is given. So properties of the graphite are anisotropic. Okay, for example, it has two thermal expansion coefficient parallel to the c axis also and parallel to the a axis. So c axis you can see here from the diagram, and where the a axis is. So important crystal parameter here is La and Lc. So La is crystallite diameter and Lc is stake thickness. Okay, so our length values along a-axis. Basal plane. So here again the basal plane concept came, through which the glide will occur, and c-axis of the crystal. So La is a measure in terms of the diameter of the equivalent sphere. Okay. So here if you will see, the sphere kind of a shape will form. So that will take the diameter equivalent diameter of the equivalent sphere. So here basically the area of the graphite crystal is measured in the form of diameter of an equivalent sphere. So this is here also you can see that yeah, this is the question. So do you guys know that how many carbon atoms do we have in a graphite unit cell? Anybody?
Four, four.
Okay. So do you know how this four term will come? The calculation.
It comes from the counting of contribution of elements in the basal plane and on the in like in the body.
What?
It comes from the counting of the contribution of atoms present in the basal plane and
Okay.
the contribution from the body centered atom.
Okay. So yeah. So basically it is all the contribution, I mean the sharing of your atoms, how your atoms, where position of your atoms are sharing with the other atoms, right? So for an example, so okay, let's say if I will tell you a very simple example of a SCC. Okay, so in SCC what will happen, the crystal structure, how it will look? Anybody remember? Anyone? Okay, let me. Do you know this thing? Hello, hello, hello. Hello. Do you guys know this? How many atoms in the simple cubic and BCC and FCC? Hello, am I audible or?
Yes, sir, we can hear you. Yeah.
Okay, so could you, do you know? No? Should I explain or not?
It is 8 atoms, sir.
So how it will
Yeah.
share? 8 atoms, how it will share the corner atoms? 1 by
Oh,
hmm 1 by
1 by 8, I think. Yeah.
1 by 8. So do you know? Okay. So okay, fine. I think nobody is responding, so I think I should. So this is one atom. Okay. So suppose how it will share one this side. Okay. One atom,
Mm.
one will come this side, another on top of this, another here. So one, two, three, four, and the other side will also the same thing. Okay. So the total will come 4. So it will 1. Again, for the BCC at the center, so it is not sharing with anyone. So for the 8, 8 into 1 by 8 plus 1.
Plus 1,
So
2,
how many? What?
2.
What?
The
2.
2.
Yes.
Yes,
So
sir.
in BCC, how many atoms are there?
2.
2. Now in BCC unit cell 2, now we will go on FCC. So in FCC, what will be there? Here, 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 and one front and again back. So what it will be? Okay.
Uh,
So 8 into 1 by
8.
8 plus in the faces how many atoms are there? Count the number of atoms which I just drawn. How many faces are there in a cubes?
4.
How 4?
Sir,
Huh? You know na, right?
6 items. 6.
6. 1, 2,
Oh,
3,
sorry,
4,
6.
and one in front, one at the back, right? So 6 atom. Now this 6 atom will share with how many? This will only share with the one unit cell, right? So 1 by 2. So 2, 2 3 are 6 and 8 and 8. So 3 plus 1 how much?
4.
So in BCC unit cell how many atoms are there?
FCC, sir.
Ha, 4 na.
Yes, sir.
So I mean I'm just wondering that are you guys found it like something which is coming very new, or are you guys, do you guys know this thing? I'm just because this is very,
Sir, sir, I know these things, but sir,
you forgot or
because
what?
I have previously told that, sir, I have an accident, so I am not able
No,
to
no, that
study.
that's fine. I'm not saying that it happens,
But sir, I
but
know
sometimes we you
everything,
but
sir.
what I will say you guys to please brush up these things. It will make you better.
Yes, sir, sure, sir.
Okay. Others also please do the same.
After that, sir, we have also calculating the atomic packing factors.
You have to know
Yes,
all
sir.
these things. These are basic. Wherever in the exams you will go, you should know.
Yes, sir. Value of
This is very basic. Just try to read sometimes. It's not, it will not take much time.
ye-
So
yes, sir.
just
Yes, sir.
so okay, fine. So okay, but it's fine if we are going little bit, but we have to move very gently so that we should clear all the concepts, right? So the diameter of the equivalent surface was the answer for this that question. But now again, let me get my pen. Yeah. So this is the thing which I just explained in the slides. What was the um, arrangement of in RG? RG and just I explained RG and HG, right? So what was the arrangement? AB, 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 ABC, BA, or ABC, ABC, AA, B, B, CC, what? This is for what? This is for what? Which G? HG or RG?
Sir, HG.
So, what will be for the rhombohedral RG?
ABCA.
ABC, ABC.
Yes. So again, just I have explained a few minutes ago, if you can see here.
Yes, sir.
So this is, you will see A, how in a one pattern A atom will arrange, B it will come like this, and C it will come. Again when it will come to the A, so A it will come, so it will come parallel to this. Okay, sorry,
Yes,
this.
sir.
And again it will go like this. But in case of hexagonal, you will see that is a AB, AB. But here it is ABC, ABC. Okay.
Yes, sir.
Now, during graphite rod manufacturing, using needle coke, the pores can be filled using what? So you know, right? The graphite rod. If you see the graphite rod manufacturing, suppose this is your something like, and this is your graphite. Okay. So the pores can be filled using what? So now the terms, again two terms will come. First one is your resin. The second term is your pitch. What? What is resin? What is pitch? Who will answer?
Sir, resin is basically we can use to harden our sample.
That is fine. We can use for many things. But I am asking,
Yes,
what
sir.
is resin? I mean, have you seen resin? It's just a kind of a binder. Okay, you can
Yes,
vary
sir.
the viscosity
Liquid
and you can
form.
use somewhere.
Epoxy resin.
So here, yeah, I said not just a kind of a binder. So here, if you will see the grain of needle or coal tar pitch coke are used with a binder for manufacturing purpose. So everywhere you will go. So now again, this will come. The term called binder. Binder is very important. If you know this, if you are reading this carbon thing, then whatever you are manufacturing, you have to use your binder material. Whether you are making a solution or composite or anything. So binder will provide you a good property. Okay, it will just, suppose it's just like a, suppose you have a carbon atoms. This is your carbon. Okay, so if you have a binder, so suppose if you have binder, suppose this is like a binder material, right? So that will create, and that will give you a good property, that will make a good surface property, good I mean it will affect your surface tensions. So your whole material, you know, this will have some unique property. You can also call it a composite. Sometimes we use a polymer in carbons. Okay, so this will attach your particles. This will bind your particle. So you have to mix your binder in some solvent in which you can dissolve, and then you add your carbon. Okay, so this will give you a composite, which is you call carbon composite, and this will have a very good property. Now the binder, so again the binder is what? Resin. So sometimes we also use as a resin in polymers and all. So with high viscosity and ability to harden due to cross linking. Okay, so it will have some cross linking effect, and that will harden your material. So here your all the material will become harder, and all the particle will get properly stuck. So it can be a resin or pitch. The mixture of binder and graphite particles can be given a shape. Example, so now suppose if you have this thing, right, what I said you, if you make some binder and solvent and carbon, this all material, and if you will uh, 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 if you want to take, you know, some structure, if you want to make some structure, then you can take your whatever the composites via extrusion, vibromolding, cold isostatic pressings, or whatever. You can just simply cast in the glass slide. You can make something like a sheet. Okay, you can do some extrusion and you can make something, some good design like this. Okay, or like this, whatever shape you want. Now the further detail course will be covered in the raw material. So these are the things. So basically the high viscosity, here you can see the high viscosity resin. So during the graphite rod manufacturing using needle coke, the process can be filled using the high viscosity resins. Okay, clear?
Yes, sir.
Now needle coke is what? Do you know what is needle coke? Oh, okay. So hmm. So now, okay, I will explain this slide. If all non-carbon atoms are removed from hydrocarbon, carbon can be obtained. Okay. Suppose hydrocarbon is what? What is hydrocarbon? Huh? Hello? So hydrocarbon is nothing but the composition where, I mean, your hydrogen and carbon both will present, right? So basically that is called the hydrocarbon. So carbon can be obtained. How? You can remove the non-carbon atoms, right? So some natural materials are high in carbon content, but in the form of hydrocarbons and with impurities. These are common residuals of petrochemical refining. Examples: coal, coal tar pitch. Okay, so here you can see the your coke and coal tar pitch. So here, if you will refine, you can also get the carbon. So what is coke? So if you know that in the plant, there is a separate coke oven. Okay, that is called a coke oven. Okay, there also you will get the carbon. So coke is non-graphitic solid which is graphitizable, that is can be converted to graphite. So coke is nothing but this is non-graphitic solid. It doesn't have anything related to the graphite, which is graphite. I mean graphitizable. Okay. So what does that mean? It can convert to the graphite by some process. So coke is pre-treated to produce needle coke, which is used as a graphite precursor. Now you know. Now you got some idea that what is needle coke. Hmm? Suppose if you want to make a graphite, suppose anything we want to make, we need some precursor. Okay, so how we will get that precursor? Even though if we want to manufacture or get the graphite, then we should have the graphite precursor. And what is that precursor? Needle coke. And how it will be produced? By pre-treatment of your coke. So coke is pre-treated to produce needle coke. And coke can also be derived from coal tar pitch. So here you can see in the second image, this here, this is your coal tar pitch. So this is, you can see, kind of a very highly viscous, sorry, very, it's kind of a gel coal tar pitch. So from here you can get some coke by processing it. Coal tar pitch is very high viscosity liquid obtained as a residue after distillation of coal tar. There are often types of pitches. All of them contain a complex mixture of aromatic and aliphatic hydrocarbons. Again, the term called very your plus one, plus two. What is hydrocarbon? How many types of hydrocarbons are there? Aromatic, aliphatic. Example, mesophase pitch, mesogenic pitch, petroleum pitch, isotropic pitch. Damer. So if you know this term, damer is very well known. So used for a road construction. Okay, is classified as pitch. So it is a type of a pitch, damer. So which we use, I think you know na damer, which you use for the road construction. And pitches are also used for making carbon fibers. So basically the needle coke is something which we use for to manufacture the graphite. We use needle coke as a precursor, and this is nothing but the pre-treated, which is coke, pre-treated coke to produce needle coke. So it is nothing but the pre-treated coke. Clear? Clear or not?
Yes, sir.
Okay. Now, in the froth flotation process, impurities are separated based on what? Guess, guess, or tell me.
Specific gravity.
What is specific gravity? You know the effect of gravity? Huh? Okay, let's say um, if you are in the earth, if your weight is around, suppose let's say 60 kilogram, then what will be your weight in the moon or then another planet? It will be the same or it will be the different? Hmm? Tell me.
It will be different, sir. Yeah.
Yes, it will be
Yes.
different. Why? Because the gravity will change. So here it is nothing related to that. I'm just asking as a general question. But here, I mean, it is something related to the density of your material. Okay. Suppose, let's say if you take an example of your water, then the density of your water, it very specific or very particular temperature, right? So it is how it will take your density of your whatever the material divided by density of your water. So in this way you can find you can do this exercise to find the uh, specific gravity of many atoms. Suppose if you will say, let's say it is like carbon, so carbon dioxide, so you can try the specific gravity is very less for that. Okay, for the polymers, some polymers like rubber, it is little high. Okay, so you can do this exercise like to calculate the specific gravity of your material, like you can say iron or gold. Okay, so let's talk about the flotation. So here, so that was not
Sir,
the
what,
specific gravity. I just told because somebody said, yeah, yes.
sir, what is the role of spiral in tabling gravity?
What
Sir, what is the role of spiraling and tabling?
role of what?
Spiraling, spiraling and tabling
Where it is? Spire?
based on gravity, sir.
Huh?
Based on gravity.
Huh?
Sir, I can't understand.
I don't know. I'm I'm not getting your point. Please repeat.
Sir, spiraling and tabling.
Okay.
Yes, sir. The
So what you
particles are
want to?
separated based on the gravity, sir.
Huh.
How? So,
Okay.
sir, this line,
Okay. So okay, let's we will discuss this slides and also I have some few content, so we'll discuss that. Apart from that, what then it will come. So let's firstly discuss this. So yeah. So there are a lot of steps, but here I will let's firstly talk in this manner, then I will also explain from the starting. So separation based on aerodynamic behavior is what? Air classification of the particles. Okay, so in the I mean what to say, I do not know the to say, you know that grain, rice grains. So it speaks I mean in the village that fan will fan will be there and the rice grain to extract the or the peels of that grain. You just have to, because of the higher mass, the one will come down and the lower mass, the whatever the peeling or the peels are there, that will come out. Okay, so due to the aerodynamic behavior of the particles, because every particles has their own aerodynamic behavior.
It is harvesting, sir. Rice.
Huh?
It is harvesting. Yeah.
Yes, yes, yes.
Yeah. Rice
Right.
harvesting. Yeah.
Right. You are right. Yes. So I was forgetting that. So floating particle in a chamber with rising. Okay. So floating particle in a chamber with rising airflow, bottom to top. Okay. So there will be airflow from the bottom to the top. Floating particle will be there, and airflow can be pulsated based on the weight. So again, the again the same thing came. Based on the weight, particle will get separated. The same thing which we often saw our grandparents doing these things to extract the rice from your, I do not know what you said before getting the rice. So we have to get rid of that pills or the outer layer, okay, and get the rice. So the outer layer will get move off because of its lightweight, and the rice will come down. Okay, so when we um, switch on our fan, very high speed fan. So this is like a air classification through air. Magnetic separation. Okay, so use of magnets. Suppose if your material is having a composition of the some magnetic and the non-magnetic kind of a material, then how you will separate this? You can use some a big magnet, so all your magnetic particle will come and stuck. I mean, come and stuck with your magnet, and then other will get separated. Now the term comes here, froth flotation. So floating impurity using suitable frothing agent. So here suppose we use some agent or some chemical it is there, we mix that. Okay, so now some, if two materials are there, one material is like the hydrophobic or another is hydrophilic, then based on the hydrophilicity of that material we can separate this material because we have put some frothing agents. So in air bubbles are passed through a suspensions, the hydrophobic impurities, okay, so the impurity which is hydrophobic in nature will get attached to the bubble and it will float, and your material which is hydrophilic, that will be at the remain at the bottom. So in this way, in the froth flotation you will get separate. So here you can see in the diagram, yeah, here. So suppose uh, this is your impurity, this is your impurity, right? This black thing is, okay, sorry. So air will come here, okay. So now if you will put some air, and here you have mixed with your frothing agent, right? Frothing agent here, like here they have given the soaps, or example sodium laureth sulfate, sodium luryl sulfate, etc. You can use as a frothing agent. So these are your hydrophilic impurity, and this is your froth with graphite. So the impurity which is hydrophobic in nature will get attached to the bubble. So here you can see I mean okay, sorry. So these are the bubble. So with the bubble your material will attach, and yeah, and the I mean the material which you want to separate, that will come at the bottom, right? So this is on the basis of your hydrophilicity. Third step is refining. After separation of primary impurities using one or more of these methods, minerals is cleaned via physical or chemical process, acid, lynching, roasting, microwave treatment, that we will take in the another slide. I will explain this process because this is very um, close to my um, interest, and how you will get separate, and it is very good field of to explore, and very few researchers work in this field. So hydrophilicity. Now, which of the following are types of the natural graphite ore? So again, do you know this? If you have been through the lecture, it's just a name. What are the natural graphite ore? Okay, I will give you a hint. One is not the natural graphite ore, so all the three are there. So you can just exclude one. Okay, tell me which one is. Hmm? Tell me. Is Kish is the natural graphite ore? Yes or no? Okay. Flake is ore or not? So these three are natural graphite ore. Okay. So in the graphite ore, just wait for 2 minutes. Just coming. Okay. Yeah. So hmm. So the major so graphite. Okay. So this is very exotic material that we are using in our day-to-day life in a various applications. So the important thing is, if you have something very important, then you should know that from where it is coming, what is the origin of that material. So the major producer of producers of this graphite material is China. In China, a lot of scientists and a lot of people are using this graphite or this I mean graphene based material for their various kind of applications. In Brazil, India is also one of them, and Mozambique, Ukraine, Russia, Norway, Pakistan, Sri Lanka, etc. So graphite ores is what? There is a three classification based on the flake size and purity, right? So first one is the vein. So how it will vein graphite? So it is the lump form. So largest crystal, it is in the form of large. The crystal size is large, and it is more than 98% pure and rare, and it is inexpensive. Sorry, it is expensive, not inexpensive. It is very rare to found, and it is very expensive because it is highly pure. flake graphite. So here it will come in a flaky form. If you have known the flakes, I have some images of flakes of graphite, but in the next class probably, if I remember, I will show. So medium crystals, so which has your what it is, the purity which is lesser than the vein graphite, which is around 80 to 95% and most commonly used. And in amorphous graphite, the powder containing very small crystals, high ash content and less than 85, so it is very less pure. Okay. And graphite ore contains clay minerals, so impurities which may be physically trapped between layers or form weak bonds and get tangled due to their micro textured surface. We need to remove the impurities without reducing the crystal size and without inducing defect. So this is very important. Okay. So in order to make the good quality product, you should not have the impurity content, as well as it should have a with the crystal size should remain the same. It should not that you are removing the impurity and your crystal size is reduced. No. So with, and also the effect should not induce. So your purpose is to get it pure without reducing the crystal size and without any inducing the defects. Now the ore processing is primarily physical separation impurities, which is we called beneficiation. Okay, so where we separate the impurities by the physical means and we get a pure material. We need to control the surface property of different components to ensure a good mixing or the separation. So this are given some thermodynamic formula. So vein, flake graphite and amorphous graphite is your three types of natural graphite ore. Okay. Hello.
Okay, sir. Okay, sir.
Okay. Yeah. Again the same thing came. Which of the following is true about rhombohedral graphite? So I have explained you. So now you can answer this very quickly.
ABC, ABC, sir.
Okay. One more factor will also be there if you know.
It is
Okay.
formed due to gliding of hexagonal graphite.
Gliding of hexagonal graphite. Yes. So yes. So basically ABC is there, and also so here it is like a graphite. Sorry, graphite basal plane is the main gliding plane. Okay. So here in this rhombohedral, consider stacking fault. So since can be formed glider twinning. So graphite basal plane, okay, through which the main gliding plane is there. So it is formed due to the gliding of hexagonal graphite basal plane. Okay. So ABC and formed due to the gliding of the hexagonal graphite basal planes. Now, can we perform casting of molten graphite to give it a required shape? Have you heard about the mold casting of your graphite? Yes. If you remember the phase diagram or what temperature it want.
Generally, to convert the graphite, it required around 2800 degrees centigrade.
It It is very, very high temperature.
Yes,
So
very
we
high temperature.
cannot
2000.
perform casting,
Yes.
right? So there are many methods, so which you have to take if you want some shape. Okay. So casting we can't do. We require very high temperature. Now again the next thing came. Graphite has hexagonal closed pack crystal structure. I have told a lot about crystal structure. So is it a true or false? True or false? Hmm. I have explained now in few slides. Specifically, I told. Okay,
It is
so
true, true, true.
Sir, true.
really, it is true. It is false. So please be aware. So tell me, what are the crystal structure we have in our graphite? Two types of what? So first one is your hexagonal, but remember this is not hexagonal closed pack. It is hexagonal graphite. Okay, hexagonal closed pack and hexagonal, there is a difference. In a hexagonal term, if you will say, so in suppose if you know the graphite, there is a layer. Okay, so there is a separation of your layer. So suppose this is A, this is B, this is again A, this is again B. So there is a separation. There is a separation of your layer between A and B. But in HCP you will have no separation. Why no separation? Because it is closed pack. Okay, so it is not HCP. It has some separation there, so it is hexagonal but not closed pack. So now it is clear.
Yes, sir.
Hmm. So yeah, here also you can see this is your SCP. So here you can see it is a closed pack. You see there is a no separation, right? And
Yes,
here,
sir.
can you see the separation of between two layers or not? Okay. So here also you can see that you can see the separate na right between two layers.
Yes, sir.
Here it is not present. It is impossible to have edge and screw dislocation in hexagonal graphite. It is possible or not? Huh? So here dislocation in graphite crystal, if you know, so this is your screw dislocations in your sorry. So this is your screw dislocations. So more common dislocations in graphite crystals are what? One, where the basal plane glide. Okay, so dislocation where the basal plane glides on each other. So Berger vectors is parallel to the basal planes here in this graphite. This is because of the weaker bond between the layers. Basal dislocation typically contain thrombohedral graphite element, and hexagonal graphite structure is retained after a few atoms. Primary dislocations can contain one triplet layer of RG, two triplet layer that overlap, addition layer inserted in the parts of your HG stick. So it is mainly saying about your structures, how it is arranged. Such dislocation may extend to multiple layers and appear as a crack on the crystal. Weaker links can also lead to non-basal faults. So screw and edge dislocations are also possible. Okay, so both the dislocations are possible here. Okay, so here in the I think this one is your so this one is I think your edge dislocations, and here it is showing your screw dislocations. So it is false. Himalayan graphite is known for its large size of graphite crystallite. True or false?
It is true, sir.
Yes.
Yes.
So if you know this, so here I have explained that India produces 50 to 20% of world's graphite. So Himalayan graphite is known for its large crystal size.
Yeah, due to high temperature and pressure, it is being formed.
Yes, yes, it is high temperature and pressure. So this is very geologists have a very high interest in this. Okay. True. Heat treatment of certain polymers can yield polycrystalline artificial graphite. True or false? So in this, the synthetic graphite, how it will produce? First one is heat treatment of pre-processed petrochemicals. Precipitation during steel making, which is kiss graphite. Heat treatment of polymers. Hot pressing of vapor deposited carbon. So in all cases, graphite is produced in its polycrystalline form. Okay. So in all cases, so all types of, so here you remember in all the cases, it produced in polycrystalline form. All types of carbon materials are difficult to machine due to hard and brittle nature. Okay. It's challenging to give it complex shapes due to anisotropy. So it does not melt, so forming techniques are not useful. Extensive sintering or milling can lead to loss of crystallinity. Solution is what? Manufacturing with graphite is done along with the material preparation. Graphite precursors are milled to microscale particles and mixed with a binder. Binder is also converted into graphitic carbon via heat treatment. Okay, so binder is also converted to graphitic carbon. Some carbon materials are precursors are not graphite but are graphitic or graphitizing. So it is true that heat treatment of certain polymers can yield polycrystalline artificial graphite. Here you can see na graphite is produced in its polycrystalline forms in all cases. So even if you do the heat treatment, you will get that. Isotropic pitch can yield highly crystalline graphite compared to mesophase pitch. True or false? Hmm? True or false? What? Say something. So mesoferrous pitch here you can see contains optically detectable spheres of anisotropic graphite structures, and this is, does not feature any graphitic crystal structure. Okay, so high crystalline isotope can yield high crystalline graphite compared to mesoferrous pitch, does not feature any graphite like crystal. Okay, so it is false. Is false. Okay, now the things which I wanted to explain at the last is that the graphite ore processing. Okay, suppose if you have a graphite, then from the graphite how you will get a, from graphite ore how you will get a graphite. So there are many process. So first one, the graphite ore processing steps. So we utilize the physiochemical properties such as specific gravity. Okay, magnetism, surface characteristics, example, hydrophilicity of the ore and the impurities. So by using these properties, we can process in order to get rid of the impurities. So beneficiations may involve the following steps depending upon the composition of the ore. So first one is your comminution. Okay, so in comminution, first one is crushing. So in the crushing, converting the rock into smaller pieces. So here you will have a big rock or the graphite ore. So that will convert into the smaller pieces by mechanical force. So here you can do some shear force or the impact, or you can apply some any mechanical forces. Then after crushing it, you will go for the grinding milling. So with increased shear stress and the lower compressive stress to avoid damage to anisotropic crystal. So milling may be done using water, attrition milling, tumbling are also used. Okay. So in that you will have some impurity separation. Step 2. So first one is what? Gravity concentration. So every material has different mass. So jigging is a method to separate components based on its specific gravity. So every material has its own specific gravity. Okay, so a jig screen will be there, a layer of large particles. Okay, so here when you will do a jig concentration, here you can see, so here the small particles are coming right from this pores here, here and here, and bit particles will remain. Okay, so in this way you can extract the particles, or you can separate the bigger and the smaller particles. Now your heavy media, sink and float. Okay, so how it will do? Immersing the sample in a liquid with intermediate gravity between the components. Lighter component will float and the heavier will dip down and it will sink. So this is your heavier and this is your lighter, so it will float. Okay, so somebody was asking spiraling and tabling, right? Who was asking?
Sir, yes, sir.
Yes. So spiraling and tabling. So ceramic spiral or table will be there with impact. So that separate the particles based on the gravity. Okay. So there will be a, so here the spiral will come. So every material will have the based on the gravity, the particle will get separate in your spiraling or tabling. Okay. So you can, if you want to know more how it will be done, if you want some video or animation, you can watch some YouTube video, there you can easily get.
Okay, sir.
Okay.
Okay, sir.
Now this I explained the froth flotation. So here the air will come and you will add some frothing agent. So due to its hydrophilicity property, the material which is impurity that will attach to your froth and the other material will come down, right? Step 3 is what? After separation of primary impurities using one or more of these methods, mineral is cleaned via physical or chemical processes: acid leaching, roasting, microbattery. Other processes are also there: electrostatic separation, film flotation, flushing. Industrial requirement of graphite cannot be fulfilled by natural graphite. Natural graphite may contain large amount of impurity. Beneficiation may be expensive. There is no control over the crystallite size and the defects. Okay, so in this way, after this all, you can see that yeah, how you will get this uh, your pure material from the graphite ore, pure graphite from the graphite ore. So I hope that it is clear. Do you have some doubt?
No, sir.
Yes.
We'll go through, sir. If any doubt, I will next class will let you know.
Sure. Anytime you can come with the, and I will also suggest you to please come by reading some basic material science like some crystal structure. It will helpful for you to better understanding, right? Because it will also for me from the starting. If you have some doubt related to that, that we can discuss also in a later class. But like closing, I mean this or how it will be, how many atoms are there in closed pack or FCC or BCC, that you should know.
Sure, sir.
Yes, sir.
Yeah.
Okay. Anything else? Vikas?
No, sir.
No?
If there is any doubts, I will ask in next lecture.
Okay. Sure. Anytime you can ask. So
Sure, sir.
it is, I hope that it is going fine, right?
Yeah, sure. Yes, sir.
Okay.
I think it is clear now.
Okay.